Today we're going to go over Chapter 7. Chapter 7 in your book is all about the data link layer. Remember way back when we were doing the OSI model and it seemed like everything was going along progressively. We'd go from layer 7 down to 6, 5, 4, 3. And then we get to 3, we just spent a whole chunk of time talking about IP addresses, subnetting, classful addresses, and whatever the case was. We will continue Chapter 6 throughout lab. But mostly through lectures, we're going to be going from Chapter 7. And like I said, I'll be jumping to the iOS chapter after this chapter, okay? Then we'll come back, finish up the physical chapter. There is a chapter, Chapter 9, called the Ethernet chapter, that I always make an extra credit chapter. I think it's well beyond most students' purpose for this course. It gets into some slot times, back-off timers, and it's very, very technical. Stuff that I wouldn't ask any network administrator to know. I would ask a network engineer to know, and none of us fit that category, including myself. If you are going to become a networking student here at Corning, you'll be a network administrator, and most of your job is going to be basically troubleshooting and documenting. Rarely ever will you have the opportunity of developing interface cards and have to deal with back-off timers or slot timers. Okay? So it's very technical. I usually skip Chapter 9. I will sign Chapter 9 over your Thanksgiving break. And the Chapter 9 assessment is an extra, let's not call it extra credit, it is a substitution assessment. So if I drop 3 of your lowest assessments, which I'm not sure, it's either 2 or 3 of your lowest assessments from Cisco, I will then take Chapter 9 and replace it. So for instance, say if you got 4 zeros, this is all hypothetical, I have to look at your syllabus. You get 4 zeros, I drop 3 of those zeros, and then you decide to do Chapter 9. You should get at least a 25% chance because it's always usually 4 multiple choice questions, right? Well, then I'll replace that 0 with 25 points. So substitution, makes sense? Chapter 9, that'll be done over Thanksgiving. So we're getting close to Thanksgiving holiday. I'm going to be looking at Chapter 7. I believe it's Chapter 11 for the iOS. And then we're going to go back to Chapter 8. Then you guys are going to hit Chapter 9 on your own, and then we'll finish up with Chapter 10, planning the network. Okay? We are getting close to the end of the semester. There's only 5 weeks left, and out of those 5, I only have 4 to cover. Question?
Just about like the weather and stuff. If for some reason I lose power for like a week, what would they do about like students that lose power that have like computer science? Would they expect
We don't care. Just make sure you guys go out and buy a generator. Your grades are more important than anything else.
I didn't know if they'd like expect you to like find some way to do it. Like, I didn't know if they had.
You know,
Like, we have to deal with weeks somehow.
we're changing the guard, so the rules are changing all the time. We have a new president, we have a new dean, and to be honest with you, I can't answer that question. I'm hoping the power isn't out that long. I know last year we had those flooding circumstances, and they sent an email to us as instructors and said, be understanding of your students' consideration. The nice thing about what I'm doing this year with the video is that if that should happen to you guys and you're in one of those areas that they list in the newspapers, then I'll make considerations and I'll work with you, okay? So remember, look after your own well-being. Your education can come later. What good is it if you're dead, right? So I'll work with you guys. Just don't try to abuse it and take advantage of it and say, you know, I was in sunny Florida and the weather is bad, you know. So we'll go from there. Like I said, we've been going down through the OSI model. And just as a little review, since it's been such a long time since we actually seen this, the very top layer, layer 7, is what? And what's the layer underneath that? In the interest of saving time, I'm just going to abbreviate these. And what's the layer underneath that? And what's the layer underneath that? I'm getting ready for your final. I know it's 5 weeks from now. As I'm looking through the final, it's like, I would say 70% of the questions on the final is all about this. If you guys know the order and which purpose each layer has to fulfill, you're going to get 70% of the material. I mean, it's just amazing that network fundamentals is all about this model here. And you want to think of it as a roadmap. You're sort of like gauging it along through the course and you're understanding each topic. In other courses like Cisco 2, you'll just be focusing on just this layer right here, which is what? layer 3, stuff that we've been spending a lot of time on. The network layer. Now, I usually write these out because, truthfully, the transport layer, the network layer, and maybe part of layer 2 is all the roles of a network administrator. These layers up here are probably programmers, software developers. And then the layers down below are probably more like engineer layers. So what's layer 2? Data link. And the last layer? Out of all the layers, the physical layer is definitely engineering. Okay? The nice thing about the OSI model is that we can be making changes up here, and it's not going to affect those layers down there. Why is that? Like, for instance, we're going to be moving from IPv4 to IPv6. Is that going to affect something down here? Why not? We segmented the responsibilities, and we said as long as the connection between layer 3 and layer 2 is observed. So whatever changes they make, they still make it compliant with the data link layer, then whatever happens from there down isn't going to be affected. So when you guys switch over to IPv4, are you going to have to buy a new network interface card? Absolutely not. Will you have to do a software update? Most likely it's already done for you. Windows 7, Windows Vista, and I think part of Windows XP now handles IPv6. You had to install the protocol.
Is it in use yet, or
Yeah, certain companies like Comcast and I think Time Warner are now issuing IPv6 addresses to their clientele. And it's just sort of like, we'll do it a selected market, see how well it works.
I was so bummed to find out it was X. I was hoping there would be like 18 and not 10.
No, thank you for that. Because remember, it's 128 bits, and there's no way in hell. In fact, when we start looking at that and we determine subnets, I don't think we're going to really need to worry about subnets, but just in case we do subnetting, we'll look at it in a hexadecimal format. So you might say subnet A, B, or A1, B1, which is going to be a lot user-friendly than it is in binary. I mean, after all, we look at the binary, you only have 2 choices, correct? So you need more bits. So it should be easier for us to actually decipher, if you will. So what's going on in the data link layer? The data link layer is comprised of 2 sublayers. The actual logical link control, LLC, and the media access control, MAC. Now before I get into the nitty-gritty theory of the data link layer, layer 2, I want to actually break it down into analogy. Let's just, it's sort of hard to put this in words, it's better to see it in drawings, but let me just map out what I'm going to do by saying it first. I want to get away from just that theory and networking stuff because, to be honest with you, your networking experience is probably very low. You're not out there building elaborate interconnected networks yet. Most of you just have home network experience. You go out and buy Ethernet equipment. Just because it says Ethernet, you're good, because now you can go around and buy anything that's Ethernet and plug it together and expect it to work. You don't configure IP addresses because one of the devices that you bought probably hands out IP addresses automatically. Occasionally the numbers are wrong, and you might have to call tech support, and you have to fine-tune it. That's probably about the extent of your network abilities. Very seldomly do you guys go out there, go to your neighbor's house, and establish a network between you and your neighbor, which we call a wide area network, correct? We join multiple networks together. And so what I'm about to show you guys is going to be something away from networks, but to give you a better understanding of this analogy that we're all familiar with. And that is our own infrastructure, our highways. And I'm a firm believer that our internet connection should be a public utility. In fact, we should have like a PBS of internet service, that every home in America has like 5 megabits per second that's paid through by taxes. And if you want something better, you pay more for it. Just like our highways. Those are public utilities. And who maintains our highways? Department of Transportation, correct? And if you guys want faster connections and more lanes, you choose to take toll booth, toll roads. We good about that? So let's look at this infrastructure that we've been using for the last, maybe 100 years or so. And I know this is a shoddy drawing of my house. And I live out in the country. And my driveway is pretty long. And my driveway is about the width of one car. Now I make this point because this driveway is shared. It's shared with everybody else who lives in my house, correct? And there's about 7 people that live in our house. And we all have our own vehicles. Now if this driveway is about the width of a car, and it's nice and long, what do you think will happen when I go to leave my house and somebody else is coming home? Yeah, we don't drive very fast on that driveway. One person has to back up. Now in computer technology, terminology, networking terminology, we call this a half duplex. That means traffic can only go in one direction at any given time. So if I'm leaving my house and I'm taking up the road and I'm beyond halfway, if you will, then it's going that direction. If somebody's coming in at the same time that I'm leaving, there's going to be what? A collision. And that's the terminology that we use when it comes to networking. That when a signal is traveling down a medium, a pathway, and another signal is traveling down that same pathway, they're going to collide. It doesn't work out for both parties, the sender or the receiver. Now my driveway obviously is connected to another road. Like I said, I live out in the country. The road that we're connected to is a dirt road. And itself is also very small. It's about a width of 1.5 vehicles. But in any case, you can't get 2 vehicles going in opposite directions to travel at the same time. One just pulls off, they get around each other. It's a price you pay to have your own privacy. And all my neighbors, granted, miles away that they are, use this same road. And they too have driveways. And most of the driveways are about the width of a vehicle. Eventually, this dirt road connects to a wider highway. This is called a logical topology. I want to talk about the behavior in which data is transmitted across this network. Just like the behavior of how we drive our vehicles. There are rules that we follow. You show to us that you understand these rules by taking a driver's test. Then we reward you with what? A license. Correct? Yeah. Let's talk about just this segment between my house and the dirt road. Do you think I have a stop sign or a traffic light? Why not? Why wouldn't I have some form of controlling this problematic situation? There's 7 of us. Let's imagine if there's 100 of us living in the house and we all had 100 vehicles. What would happen to the probability of us having a collision? It goes up. So the more users that are using a shared medium, the greater the chance of collisions. What does collisions translate to when it comes to performance when we're dealing with networks? Yeah, you're going to get lost packets, so the performance is going to go down because you have to retransmit, correct? And that becomes exponential because the more you retransmit, the greater chances you're going to have collisions. So hopefully by the end of class today, I'm going to tell you about a technology called CSMA/CD. But to this point, I have no controlling mechanisms. I say you can come and go as you please. There isn't a traffic light. There is no indication that when the person comes up the road that they can see that somebody else is on this driveway to wait until that person flees. The only thing we do is we take our time. All right? What about here? Do you think there's a traffic light along each of these intersections? I mean, is it safe to call them intersections? And what is an intersection? When 2 paths intersect? Okay. So I have a connection for this main road to my driveway, and I also have another one here and another one there. And an intersection basically is a point where two opposing sides are going to meet, correct? There's no way around it. You're coming down the highway, down Spencer Hill, and you guys are going to get to Denison Highway. You cannot cross Denison Highway without running into somebody, correct? So what did they implement as a controlling mechanism down at that intersection? A traffic light. Why would they do that? Because two cars cannot occupy the same space at the same time. It's a mean for sharing. We are sharing that particular point. We are sharing that pathway, that medium. And when it comes to sharing, you have two ways of dealing with it. One's called deterministic. Now, for the longest time, this term was always baffling me. What do I mean by deterministic? Well, think about the word. What's the first 5 letters in deterministic? Determine. You can literally determine where somebody's going to be, which direction they're going to go, and a deterministic network, and deterministic control. Translation. If there's an intersection down at Denison Highway, no different than there's an intersection here, I know that somebody's going to be going either left or right, correct? And if I put a one-way sign, now with 100% confidence, I can say that anybody that leaves this road and comes onto this road is going to go which direction? They're going to go that way, correct? That's deterministic. We have control. And if we have control, we have predictability. And if we have predictability, what can we do? We can avoid collisions. Why do we want to avoid collisions?
Because they cut down on
Decrease performance.
What's the problem with deterministic control? What is the problem about having a one-way?
what if you have to go the other option?
Yeah, I live between Mansfield and Elmira. And if I want to go to Mansfield, I have to make a right at the end of my driveway, at the end of the dirt road. Can I do that in this case? So I have to make a left, and that means I got to travel 10 miles up the road, because that's the next intersection. To make another left, back travel? Yeah. So now we got to trade off distance, right? Because the more distance I have, what's going to happen to performance? The longer it's going to take me to get there, so performance comes down. 2, what? Collisions. So when would I implement something like this? When do you typically see one-way roads? And they drive me nuts when I'm not familiar to a town or a city. In big cities, right? You want to make a right and you see, do not enter one way. Why do they do that? Why do they do that in big cities? Why do they have certain roads allocated for one-ways going in one direction? If you go a couple blocks down, it's going the opposite direction. Because it doesn't save on distance, but it will save on time. Why is that? Explain to me, why did they do that? Why did they put one-way signs on back streets in big cities?
So two-way collisions. Because if you're going down an alley and someone else also decides.
If it's narrow, yeah. But what if it's a width of 2 cars? You could double the bandwidth, correct? Because now traffic is flowing in the same direction, but we have separate lanes. Making sense? So, in this particular case, if I live out in the country and there's not very many homes on there, do I want a deterministic approach? Do I want to control that? Did I put a stop sign at the end of my driveway? Are there traffic lights down through this road? No. Why not? The population's pretty low. What are the chances of actually having collisions? Very low. So I'm saying, why go through all that cost of putting in traffic lights Because nothing irritates me more often than I'm going through and I have a green light, then all of a sudden somebody trips the, signal, and then my light goes to red. Their light goes to green just to let one car by. I mean, you know how much energy is wasted? You know how much gas is wasted for me to slow down, come to a stop, to start back up again? We don't bother doing that in the country. We don't need to because there's not a lot of us. What do you think is going to happen down here, though? You think there's going to be a stop sign at least? Why? Yeah, this is 549, and it's one of the major routes that connect us to the bigger cities, if you will, quote unquote, bigger towns in our area. So there's a lot of traffic on that. And the speed limit is posted at 55, but very seldom does anybody do 55, right? Would it make sense to put a traffic light there, though? No, let's start off. Would it make sense to put a yield sign? Because stop signs are pretty good, right? Stop, count 4 seconds, and go, regardless if anybody's coming. Yeah, good morning. I know it's Monday. All right. Why did we not put a yield sign in there? Because, and I come to the state line, I go past it, and it's like 328, and I'm making a left on the Sagetown Road. This is, if you guys know the area, it's right before Pine City. There's a yield sign right there. It's a T intersection, no different than this, and there's a yield sign right there. But I have a stop sign right here. You don't have to stop for a yield unless there's what? Oncoming traffic. Exactly. But a stop sign, you have to stop regardless. Even if it's 3 o'clock in the morning, you have to stop.
You should probably slow down, but hey sign.
Yeah. Now remember, stop signs with white borders around the edge are optional at nighttime. No, please don't take that. I'm going to get a lawsuit. My instructor said they're optional at night. Now he owes me a $10,000 card plus health insurance. Now, yield size doesn't work out. Yeah, I know. Edit that one. Cut. So here we are. We have a stop sign. Do you think people on 549 would be very appreciative if we changed this to a traffic light? I know a lot of people that live on my road would love a traffic light there because it's sort of on the knoll and it's hard to see oncoming traffic. But a lot of people on 549 would be pissed off for that. So we have to settle for a stop sign because we're concerned about collisions. And networking, we're concerned about collisions. In fact, all this has been logical for you guys to be able to relate, to see behavior, to see why we do some things that are very abstract when it comes to networking, to relate to what's going on here. In real world, we can see things visually and they make sense. But in networking, we really can't see the signals that are flying through our wires or through the air to be able to understand why they're doing what they're doing. In the data link, it's all about controlling the medium. In fact, we call that MAC, Media Access Control. And so this particular, as I develop these homes and call them nodes, and get used to this. A node is a device that's connected to a network. You will have one of the most classic topologies. So this is a logical topology. Remember, when it comes to logical topologies, we're learning about behavior, how the signals are traveled, how they're controlled. This is called bus. In a logical topology, in the bus topology, we have collisions. We have no way of controlling who's sending what. In fact, we don't know who's going to send it. I don't know what my neighbors' schedules are, when they're going to be leaving their house and when they're going to come home. I have no clue. We call this non-deterministic. It's unpredictable of the traffic that comes down this main line. Since they're all connected, and if we're using electrical signals that carry data, what happens when you take a copper wire and touch it to another copper wire? You're going to get electricity, correct? Both pathways are going to have electricity. When is the current applied when it comes to networking? When do we put electricity on the wire? When we're sending data. That's what we call the carrier. In fact, we call it the carrier signal. The carrier is the physical attribute or identity that's used to send data. What do you think it is when we want to transmit something across the airwaves? What would the carrier be? If we're sending things over the airwaves, if we're using air. It's a frequency, it's radio frequencies, right? And all radio frequency is just electrons flying out at high rates. Okay? What do you think the carrier is going to be if we're sending it using fiber optics? Light. All that's covered in the physical layer. In fact, when we get back to that chapter, you guys will learn these attributes in themselves. The moral of the story, though, is if I had this main backbone made up of coax, which is what we used to do back in the day, we used to call these thick nets, and then I had little connectors, T connectors, that would tap into these, and that's what we call them, taps. They're basically all one copper wire. And the way we would draw that is simply like that. And this became your main line, the bus. And at the end of this bus, there were terminals. Because the signal would propagate, but it had to end. It just couldn't keep on going on and on. So the terminators would stop the propagation. What's the problem with this, though? When one device is transmitting, what must the other devices do? They must stop and listen. And if I want to talk to this node right here, does this node also get the message?
Yeah.
Why would it get the message?
It's on the same cable. It's on the same bus.
They're tapped to the same wire, right? And when you send electricity through that same coax, the same copper wire, what's going to happen? All the devices on that network is going to get the signal. So my question to you guys is, what does this device use to choose not to listen? It's addressed to you. It's me saying to, hey, Brian, what do you think the answer is? Now, do you notice there's a common medium that connects us all? What is that medium that connects us all? The air that we breathe, right? Without it, I can move my lips, but nothing's going to come out of it, right? Because I suck in this air, I vibrate it using my vocal cords, and that vibration produces a frequency. That frequency vibrates the particles that are in this room. For lack of a better word, we're going to call that air. These air particles are going to jam up against your drum in your ear, and it's going to beat. That eardrum converts that signal back into a language, into sound. We clear about that? Your mouth and your ears act as an interface card. Your mind has to take that high level, because we're not born with a language. You guys are taught a language. This is what we call high level. That's this level up here. You guys are programmed when you're born. Every time somebody speaks to you, to record that and try to make sense out of it. You're being taught. Then it's got to travel through some parts of the mind to translate it. And that's what's happening right here. Is that the only form of communications that we have? Take a look at my whiteboard. If I were to turn off the lights, would you guys be able to see the message if we assumed it's all black in here? No. So you guys see things through light waves, correct? But even if you were to see this, and if I were to write it in like what, Swahili, would you be able to understand it?
No.
You can translate the white waves into symbols, but the symbols have no meaning to you. So that's where the physical layer and the data link layer come together. The logical link control is the bridge to connect this high-level stuff to the physical world. And the MAC, the media access control, will give us some kind of addressing scheme. Earlier I addressed Brian. The reason why I addressed Brian so everybody heard his name is I wanted to isolate him out of this shared space. I said, Brian, what do you think this node's going to use to determine whether or not that message was sent to them? What did you guys use to determine whether or not you're in the clear? Thank God that message had nothing to do with me because Brian's carrying the burden. What was it? Yeah, his name. What if I had said, hey, student, or students, what do you guys think?
I would have jumped up to answer.
You would have? See, I should have picked on you first. Surprise, surprise. If this was Ethernet, if we decide to use the Ethernet standard for this network, Ethernet uses something called a MAC address. It's 48 bits. It's typically written in hexadecimal format. Okay? When the data link layer gets the data, the logical stuff, mapped out and gets ready to get it framed out, that's the PDU called for the data link layer. You frame out the packets. The very couple of bits, or bytes, I'm sorry, of that frame is going to consist of a machine address, a media access control address, a MAC address. In each of these interface cards, there's going to be a number burned into the interface card that you cannot change. And that number, now I say that in quotations, and that number will always stay the same no matter where you take that device to. Let's say if it's your laptop and it's mobile, you bring it here to school, you hook it up to the network. You unplug it, you take it home, you hook it up to your network. That physical address will never change. What address will change, however? Your logical address. Do you see where the logical's now coming in now, folks? Why is that MAC address important? It's for local delivery. It allows me to send a frame out on this wire, and for devices that aren't supposed to get it to ignore it, and the device that's supposed to get it to accept it. This is problematic. It's no different than me telling you guys my password to log into the website, and all I want is Marcus to have this password. But I shout it out loud. And I say, hey, Marcus, my password is DOG. You guys choose to ignore it. But did you have to? So if you weren't following the rules, breaking the code, violating the trust, the agreement, right? Because what is a network? Two or more devices connected together, governed by the same set of rules. If you decide to configure this device to listen and accept all frames, then you're violating my trust. This is one form of topology. Why do we do this? Why do we string devices along together? Go back to the 80s. What do you think would have been the reason for that? What's that? I'm sorry, you gotta say it louder. Okay. It's cheaper to establish the communication because do you see any central devices? Any extra hardware? It was all inspired by electricity. Consider these outlets. When you guys plug in your devices into an outlet, doesn't matter which outlet in the house you guys plug into. They're usually strung up like this in series, correct? And we call that a circuit. Seemed to make sense. This is logical, however. We moved on to it and we created a physical topology that looks more like this. This physical topology is a whole lot different than these logical topologies that I drew over here. What goes in that circle that connects those three devices together? Out of all the... Whoa, I knew you guys were going to say that. Just slow down. Out of all the devices that we've talked about this semester, which was the only intermediary device that when they received a frame, it would pass it to everybody else connected to it? Hub. So a physical...
Attention, Kellen.
Do you go home and watch these videos just to pat yourself on the back?
That's my hair. That's my hair.
All right, so a physical topology is actually going to tell you how to configure them together. It's going to give you the actual arrangement of the devices. Now, I took a shortcut. I drew it out using a sort of a hybrid approach because I didn't tell you where this hub is going to be located. Naturally, you might say put it in the wire rack in C002, and then some drawings will have the wires actually being ran. The moral of the story, though, is I'm actually telling you the list of devices that are used to connect them together. I will specify what type of cable should be used. I might say Cat5. You guys will learn that in the next physical chapter. I will tell you to use a hub. Now, some people want to say this is a star. I'm not a big fan of calling this a star topology. I understand why they want to say that. Because when you look at a star topology, what does all the nodes have in common?
One thing in the middle.
The center. And I can go for that. Right? I mean, it definitely changes this bus topology into that. So I could believe that. This is a star. By the way, Cisco just says for both of them, and I like this. And it took me a lot of years to actually accept this terminology. Because when I taught computer essentials, I was all about the star topology. It's the way to go, especially when you throw a switch in there. But Cisco calls it a multi-axis topology. Why would Cisco group both the star and the bus into what they call a multi-axis topology? What do we mean by multi-axis?
Just another name for network, essentially, right? Because it's like they have access to the same information.
Let's not same information, because we could add security to it. What do they have access to that's the same in all these topologies that you guys see? The medium. That's why we need to add, that's why we need to control it. Or create some kind of structure, some kind of rule that'll help give us some kind of control to the communication process. What's the multi-part then? What do you guys see more of? The nodes. And all these topologies, I have multiple nodes accessing the same medium. And because they're accessing the same medium, I have to create some kind of control or some kind of mechanism to ensure that collisions won't occur. That's deterministic. Or if they do occur, some mechanism to cope with. Okay? No different than on my dirt road, that when we see each other, somebody pulls off to avoid collisions. And if we do bump each other, we understand that happens, especially on winter days. That's why we try to drive slow. Okay? That's one logical topology. This particular topology we're going to visit again. And we're going to talk about how we improve on it using CSMA/CD. But another logical topology I want to get into is called a ring. More importantly, a token ring. If you were to draw this logical topology out, what shape would you use? So here's my logical topology. Remember, logical was all about the behavior. If you guys were to draw this out, what shape would you use? Circle, there we go. Derek, could you entertain me? We need some more attention. All right, here we go. We're going to drop off a node. Now, when I visit my brother over in Europe, they're all about this. In fact, what do they call that? When you have In fact, we have one right here in Corning. I forgot all about that. See, I always come up the back way, so I don't get the chance to drive around this nice little circle that we have. But there's that big welcoming sound, and you notice that all the access points, I mean, that's what we're getting into. Access, right? We're accessing the common medium. Have what type of traffic control mechanism? Yields. And we call these roundabouts. Europe, they love these things. In fact, they love them so much they make multiple lane roundabouts. And it makes you wonder how in the world those people actually function. And what? Yeah, you keep on going around and around and around. And now it's very commonplace for these roundabouts for people to run into each other. And they think nothing of it. I mean, they drive their cars like you guys do in bumper cars. Bump each other throughout there. I mean, when I was over there, we took a tour bus, and our bus ran into another bus. They just waved each other on, like, hey, how's it going? Bump each other all over the place to get out because we were in that inner lane, and we needed to get over. And so 5 o'clock, it was Rome, and a bunch of people drive these little cars, and this bus is like, screw you, I'm going to work my way through it. And all these cars were stopping, bumping into each other, letting this bus go through because it's like, it's fair game. Well, rings are like that. The important thing, though, and if you want to be a real asshole, you would go against the grain, right? But the traffic flows in one direction, correct? Now, when we're driving with our cars, we don't have the concept of token in mind, but we have a rule of a token, and that is we call it the right-of-way, correct? If you have a yield sign, the only time you're allowed to go is when nobody else is on the shared pathway, correct? When you can do it without getting in an accident, the right-of-way. We clear about that? So these devices are allowed to talk to each other only when they have a token. It's like a microphone. If you have the microphone, you're allowed to talk. If you don't, you have to listen. What's intriguing about it is, and it's all based off the implementation, if this node wants to talk to this node, can it go this direction? Now, it's got to go this direction. If it's sending a message, can this node now talk when the token comes over here? Because the token will stop here. Why will the token stop here when it's leaving here to get to this device? Well, it can only go that way, but why would it stop? To see if that token is the one that's supposed to get the, see if this node is the one that's supposed to get the message, correct? Because visually you guys are saying, well, it's right here. Skip this one, skip that one, and go right here. But electricity doesn't do that. If this is all the same copper wire, what's going to happen? It's going to get the signal. And what is it going to do with the signal? It's going to read the message and it's going to look for a MAC address, correct? Depending on what standard we're using, if we're using Ethernet, it's going to look for a 48-bit destination MAC address and say, is that me? If not, pass it on. All right, it decides to see that the token has a message. The message doesn't belong to it. It passes it on to the next node. What is that node going to do? Same thing. Says, it's not me. I'm going to pass it on this node. Sees it. And it says, yes, that is me. Grabs the message. What's going to happen to the token now? Remember the communication process. Sender, receiver. We have the sender making a request. What do you think that node's going to do? And it all depends on implementation. It has the token right there. It's like watching a news interview. The microphone's here to the anchor person. They're asking the question, the reporter. So what do you think of the storm that's going to happen tomorrow? Then they do what? They pass the microphone to the other person and they talk, correct? This end device receives the message and will respond and put it back onto this node. Question, if that's what happens, could it be that the only two devices that are allowed to talk to each other are the ones that monopolize those connection? Back and forth between you and me? Well, they're allowed one message per so many churns. Next time it comes around and says, look, I've already picked up your mail. Now I got to go back to the next person. This is all in implementation. Could we improve the efficiency? What do we know is true about this network? How many devices are allowed to transmit at the same time? One device, right? Are there going to be any collisions then? So what's the size of our data? It could be massive, correct? Because I don't have to worry about collisions. What about the addressing or the collision mechanisms to detect and to recuperate? Very minimal. Gives me more data room, better bandwidth, better performance. Are we clear about that? Could I string the messages along? Could I keep on adding to the message? Just keep on reading through each frame. When you find your name in the list, grab that message away. It's like a choo-choo train. It just keeps on going around and around, stopping off the way stations, and then we add or take cars off. Make sense? And we keep on doing this. And the data keeps on going around and around and around. Physically, do you think we lay out our computers in 2 circles? Would you want to do this in a local area network? Why not?
It's obnoxious.
Why? We do use them, and they're very helpful, and you guys should be very appreciative of having this.
Whatever device is talking us at the token.
The more devices you have, what do you think is going to happen to the latency, the time it takes to deliver? It's going to increase, right? Because you have to keep on waiting. It's like going to a town hall versus going to an amphitheater and having a whole Q&A session, correct? Where does this work? How about when we connect cities together? Let's say this is Elmira, this is Corning, this is Bath, and this is Podunk. I don't care. But the fact is that the data that's transmitted locally, there's going to be a lot of it. And if we can contain it in a geographical area, which we call a local area network, right? It's not going to bother internet traffic. And maybe the device you're trying to communicate with is down the road from you. And that's fine. Because once again, that's part of the metropolitan area network. Do you see this escalation? The base is really wide, and you work your way up to a pyramid, correct? At the point, you might want to connect to other devices, other connections. There's going to be a lot of data there, but few people using or having access to that, correct? So how does this look physically? This is one way. Doesn't look like that. All right, use your imagination. What makes this network a little bit different than a bus topology? Do you see how the N connects back to the beginning, hence a circle? These are great for large geographical distances. More likely or not, we'll probably be using fiber. Fiber can only transmit in one direction. You have a very tiny shard of glass that's just the size of a laser, the red laser beam, if you will. And because of that, you will have a light source on one end of it and a diode on the other. And that's going to be flickering on and off. What's nice about fiber and using the laser to transmit data? Transmits it faster and for larger distances. What's the burden about it? It's only one way. Oh, it's extremely fast, but it's only one way. But isn't that what we want here? We go from here to there. Even if we're trying to transmit to another city, like from New York City to Los Angeles, I'll just go from city to city to city, dropping off whatever load I need. Correct? Think about a train versus a car. Our car gives us our freedom to travel when we want to, non-deterministic, where we want to, when and where. A bus or a train has schedules, and they don't have very much stops. It's like a train will take you from New York City to like Albany, and it won't stop along the way. If you need to get somewhere halfway in between, you're going to have to stop at Albany and take a bus to that point, or a taxi, just like subways. You guys are getting the idea? But what's the difference? A train can handle a lot of people with zero collisions, because that train that's running on that track better not have another train going in the opposite direction, correct? It's all about control. Ring topologies are deterministic. They use a token to avoid collisions. Gives us a lot of bandwidth, larger distances, but not very flexible, like when it comes to serials. Sorry, I meant stars or bus topologies. Okay, folks? So tomorrow, if you guys come to lab, weather permitting and all, we're going to be going over VLSMs. Wednesday, I'll be going back over some topologies, and we'll look more into CSMA/CD and CSMA/CA. Read Chapter 7.